Good morning, students. Our today's topic is geodesics. Geodesics is a distance which is related to minimum distance. So what is geodesics? If we take a surface and we take any 2 points on the surface. Here A and B are 2 points on the surface. Then we can join these 2 points by using a number of curves. This is a curve joining the points A and B. This is also a curve joining the points A and B. Then the curve of the shortest distance between these 2 points, that is called geodesics. Thus, geodesics is a curve of shortest distance between the 2 points on the given surface. For example, on a plane surface, the shortest distance between the 2 points, that is a straight line. Now, there is another definition of geodesics. If we take a surface, let S be a surface and A and B are 2 points on this surface. Let us take C be a curve joining these 2 points A and B. And for the small variation, let us take C bar, that is another curve joining the points A and B. If the length of the curve C remains stationary for the small variations, then we say that this curve C, that is a geodesics. It means if we have a slight change for this curve C, then after the change, the length of the new curve and the length of this curve C, that remains the same, then we say that this curve is geodesics. So we can define geodesics between the 2 points A and B on the given surface as a curve on that surface joining the points A and B, which possesses a stationary length for the small variations. Stationary length means the length of the curve remains unchanged after the variation. Thus we can say that the geodesics are the curves of stationary length. There are so many applications of geodesics. Some of the applications of the geodesics are, we use the concept of geodesics in aircraft modeling, navigation problems, in the study of surface of any planet, and especially in the geodesic domes. Geodesic domes are the hemispherical ballast structures which are made with triangular elements with minimum material. This type of structures, you can see this is a hemispherical ballast structure and this is made with triangular elements, and such kind of domes, they are constructed with minimum material, and generally these are used in the construction of auditoriums, shelter homes, etc. Now we will find the differential equation of geodesics. So let us consider this be a surface having the equation given by R is equal to RUV. Here U and V are parameters. Let us take 2 points A and B on this surface, and let us take, there are lots of curves joining the points A and B. Then what is geodesics? A curve with fixed length for the small variation, that will be called geodesic. Thus we can say that geodesics are the curves of stationary length. So let us consider the curve C joining the points A and B, denoted by U as a function of t and V as a function of t. Let us take t varies from 0 to 1. Let us take at the point A the value of t is 0 and at the point B the value of t is 1. Now, and the curve C bar, that is another curve joining the points A and B for the small variations. And let us find the length of the curve C. Now, the length of curve C, that is given by using the first fundamental form. In the first fundamental form, we learned the expression to find the arc length, which is given by ds square is equal to E du square plus 2f du dv plus g into dv square. Now, let us divide throughout by dt square. So, this will become ds by dt whole square is equal to E into du by dt whole square plus 2f du by dt into dv by dt plus g into dv by dt whole square. Now, the derivative with respect to t we have denoted by dot. So, du by dt can be written as u dot, dv by dt can be written as v dot. So, this will become ds by dt whole square is equal to E into u dot square plus 2f u dot v dot plus g into v dot square. Now, taking square root on both sides, we get ds by dt is equal to square root of E u dot square plus 2f u dot v dot plus g into v dot square. Now, from here we can multiply both sides by dt, and to find the length of the curve C, we can integrate between the limits 0 to 1. So, we get integral 0 to 1 ds is equal to integral 0 to 1 square root of E u dot square plus 2f u dot v dot plus g into v dot square. Let us denote the length of the curve C by SC. SC means the length of the curve C, and we can see here this is a function of u, v, u dot, v dot. So, we can write this expression as a function of u, v, u dot, v dot. So, the length of the curve C is denoted by SC is equal to integral 0 to 1 function of u, v, u dot, v dot. Now, let us take for the small variations another curve C bar joining the points A and B. And this curve C bar is denoted by the parameters u bar and v bar. Now, u bar is we have taken u plus epsilon into g, and v bar we have taken as v plus epsilon into h. Here this epsilon is very small quantity, and the functions g and h, they are any arbitrary functions of t such that at the point A, it means for t is equal to 0, both functions they vanishes, and also at the point B corresponding to t is equal to 1, the both functions g and h they becomes 0. Now, let us find the length of the curve C bar. Now, as for the length of curve C, we obtained integral 0 to 1 function of, here u and v are replaced by u bar and v bar. So, the length of the curve C bar, that will become integral 0 to 1 function of u bar, v bar, u bar dot, v bar dot. Now, the value of u bar and v bar, those are u plus epsilon g and v plus epsilon h. U bar dot means u dot plus epsilon g dot. V bar dot means v dot plus epsilon h dot. Now, because for the geodesics we have the curve is of stationary length, it means we are to find the length of both curves and find their difference and equate it to 0 to get the differential equation for geodesics. So, let us find the difference of the lengths of the curve C bar and the curve C. So, from the equations 1 and equation 2, substituting the values of the lengths of the curve C and curve C bar. So this will become integral 0 to 1 function of u plus epsilon g, v plus epsilon h, u dot plus epsilon g dot, v dot plus epsilon h dot, minus function of u, v, u dot, v dot. Now the value of this expression we can find by using Taylor's theorem. So by using Taylor's theorem, the value of this expression is given by function of u, v, u dot, v dot plus epsilon g into curl f by curl u plus epsilon h into curl f by curl v plus epsilon into g dot curl f by curl u dot plus epsilon into h dot curl f by curl v dot, and so on. Now the higher order powers in this expression, those we will denote by order of epsilon square. This symbol will be used for the higher order powers in epsilon. Now let us substitute this value in the equation 3. So the equation 3 will become SC minus SC bar is equal to integral 0 to 1 epsilon into g curl f by curl u plus h curl f by curl v and plus integral 0 to 1 epsilon g dot into curl f by curl u dot plus h dot into curl f by curl v dot, and plus order of epsilon square. This denote the higher powers terms in epsilon. Now we can integrate these by integration by parts, taking this as first function and this as second function. In the same way, we will integrate this also by using integration by parts, taking curl f by curl v dot at first function and h dot as second function. So applying integration by parts, we get the difference of the length of the two curves C and C bar is given by first integral we have taken as it is, which is integral 0 to 1 epsilon into g curl f by curl u plus h curl f by curl v. Now in the second part we have used integration by parts. First function as it is, integration of second between the limits 0 to 1 minus integral derivative of first function integration of g dot, which is g. In the same way we have used integration by part for the product of the terms curl f by curl v dot and h dot. So first function as it is, integration of h dot, which is h between the limits 0 to 1 minus integral derivative of first integration of second. Now as we have the conditions for the functions g and h, both the functions varies at the points a and b. At the point a, the value of t is 0, and corresponding to that the values of functions g and h are 0, and also at the point b the value of t we have taken as 1, and at t is equal to 1 the value of g and h, that is 0. So these two terms, they will become 0, and now we can combine the terms with g in one bracket and the terms with h in one bracket. So finally we get the length of curve C minus the length of curve C bar is equal to epsilon into integral 0 to 1 g into curl f by curl u minus derivative of curl f by curl u dot plus h into curl f by curl v minus derivative of curl f by curl v dot into dt, and plus order of epsilon square. This denotes higher order terms in the powers of epsilon. Now let us denote this term by L and this term by M. So this will become SC minus SC bar is equal to epsilon into integral 0 to 1 g into L plus h into M plus order of epsilon square. Now for the geodesics, the length of the curve remains stationary. It means there is no change in the length of the curve C after the variation. So it means length of curve C bar and length of curve C, they remains the same, and therefore the difference of their lengths, that will be 0. So from here this term will become 0. Now for all the values of functions g and function h which satisfies the conditions g is equal to 0 and h is equal to 0, when t is 0 and 1, this equation is satisfied if and only if L and M are 0, and thus we get the geodesics differential equations given by L is equal to 0 and M is equal to 0. So finally we get the value of L is curl F by curl U minus derivative of curl F by curl U dot is equal to 0, and M is equal to 0 implies that curl F by curl V minus derivative of curl F by curl V dash V dot is equal to 0. So these two equations, they together gives us the geodesics differential equation. So this completes the topic geodesics differential equation.